Welcome everyone. In this session, we are going to explore the backbone of information systems acquisition and development, system development methodologies. Whether you are building custom software or acquiring off-the-shelf solutions, choosing the right framework is critical for success. We will break down the traditional approaches, modern agile techniques, and how to control these processes effectively. Let's start with the foundation, the Systems Development Lifecycle, or SDLC. Think of this as your roadmap. It is not just about coding. It is a structured management process to ensure that what we build actually solves a business problem. Historically, we called it the software development lifecycle, but today it is broader. It's the systems lifecycle, because we often buy or lease technology, rather than just build it from scratch. The core value here is control. We move through specific phases, from feasibility to disposal. Crucially, we use a gate process. You don't just drift from design to coding. You stop at a gate, conduct a formal review, and get approval. This prevents bad projects from consuming good resources. Here's the classic flow of the SDLC. We start with feasibility on the left. Can we do this? We move to requirements. What do we need? Then design, development, testing, and implementation. Finally, we review it in post-implementation. Notice the dotted lines representing gate reviews. These are your checkpoints. You cannot pass from design to development without a sign-off. This structure minimizes risk by ensuring quality at every step before moving forward. The oldest and most traditional methodology is the waterfall model. Visualize a real waterfall. Water flows down. It doesn't go back up. In this model, we finish requirements completely before we start design. We finish design completely before we write code. This is fantastic for projects where requirements are fixed in stone, like building a bridge or a regulatory compliance system. However, it is rigid. If you realize in the testing phase that you missed a requirement, going back up the waterfall is expensive and difficult. We also have the V model, which is a variation that emphasizes testing. For every design phase on the left side of the V, there is a corresponding test phase on the right, ensuring validation happens at every level. This diagram illustrates the cascading nature of waterfall. Requirements flow into design, which flows into implementation, then verification, and finally maintenance. The upward arrows show that while returning to a previous stage is possible, it is difficult and often costly, represented by the resistance in the flow. The structure mandates that you get it right the first time. Because waterfall is so rigid, we evolved into iterative and spiral models. Instead of one giant push, we build the software in cycles. The spiral model is unique because it explicitly focuses on risk. Imagine a spiral starting from the center. Each loop around represents a phase. We plan, we assess risk, we build a prototype, and we evaluate. Then we do it again for the next version. This allows us to catch a major design flaw in the second loop before we've spent the whole budget. If you are building a mission-critical system where failure is not an option, the spiral model helps you identify and mitigate high-risk elements very early in the process. Here we visualize the spiral. Starting from the center, we move through 4 quadrants repeatedly. First, determine objectives. Second, and most importantly highlighted in orange, identify and resolve risks. This is where we prototype. Third, development and testing. Fourth, plan the next iteration. The cycle repeats, spiraling outward as the software grows in maturity and complexity. Sometimes, speed is the priority. Enter rapid application development, or RAD. RAD was a reaction against the slow pace of waterfall. In RAD, we don't spend months documenting requirements. We get the users and developers in a room and start building prototypes immediately using fast development tools. We build a screen, show the user, they give feedback, and we fix it right there. It relies heavily on 4th-generation languages, 4GL, and code generators. While excellent for departmental apps and quick fixes, RAD has a weakness. It often ignores the big-picture enterprise architecture. It's great for speed, but you must ensure you don't create a disjointed system. The RAD flow is fast and cyclical. We move from concept definition directly into user design and prototyping. Notice the tight feedback loop. Here, we stay in this prototyping phase, refining constantly with the user until it's right. Then we move to construction and rapid cutover. The heavy lifting happens in that middle loop, ensuring the user gets exactly what they see on the screen. Today, Agile is the dominant methodology. Agile isn't just a process. It's a philosophy that accepts that requirements will change. We usually implement Agile using Scrum. In Scrum, we don't plan the whole year. We plan for 2 weeks, a sprint. We have a product owner who prioritizes a list of features called a backlog. The team pulls from that list and sprints to finish them. We meet daily in stand-ups to track progress. It is incredibly flexible. However, as auditors, Agile scares us slightly. Why? Because the Agile Manifesto values working software over documentation. You must ensure that Agile teams still document their controls and decisions for audit trails. This is the Scrum lifecycle. It starts on the left with the product backlog, the master list of features. We select a few for the sprint backlog. Then we enter the sprint loop, a 2 to 4 week cycle, containing the daily stand-up meetings. At the end, we output a shippable product working software. We conduct a sprint review to learn, and the cycle feeds back into the backlog for the next round. Let's look at how the code is actually structured. We moved from procedural code to object-oriented system development, OOSD. In OOSD, we model real-world things as objects, like a customer or an invoice, which contain both their data and the actions they can perform. This allows for encapsulation, keeping data safe inside the object. Building on this, we have component-based development, CBD. Think of this like Lego bricks. Instead of writing code line by line, we assemble applications from pre-built, pre-tested components. If you need a spell checker, you don't write one. You plug in a spell check component. This drastically reduces time and errors, because the blocks are already proven to work. Here we see the relationship. An object contains data and methods. Multiple objects can be built into a component, which has a clean interface. You then plug these components directly into your application. The diagram shows the progression from granular code objects to reusable building blocks that construct the final system. Before we write a single line of code or run a single sprint, we must ask, should we do this? This is the business case and feasibility analysis. The business case proves the financial value. What is the return on investment, ROI? The feasibility study asks if it's possible. We look at economic feasibility. Can we afford it? Technical feasibility. Does the technology exist? Operational feasibility. Will the staff actually use it? And legal feasibility. As auditors, we review these documents first. If a project proceeds without a solid business case, it is a failure of governance, regardless of how good the code is. This mind map breaks down project viability. On one side, we have the business case, focused on financial ROI and strategic fit. On the other, we have feasibility, branching into 4 critical checks: economic money, technical capability, operational usage, and legal/schedule, compliance and time. All branches must be satisfied for the project to be viable. Finally, we face the classic dilemma: buy or build. Today, organizations rarely build everything. If it's a standard function like payroll or HR, we buy often using software as a service, SaaS. It's cheaper and faster. We only build custom software if it gives us a unique competitive advantage that we can't buy from a vendor. Sometimes, we use reverse engineering to deconstruct old systems to understand how to rebuild them. Your job as an auditor is to check the decision-making process. Did they issue a request for proposal, RFP? Did they map requirements to the vendor's features? Buying software that doesn't fit the business is just as bad as building software that doesn't work. This decision tree guides the strategy. We start with a need. We ask, does this provide a unique advantage? If yes, we go the custom build route and use the SDLC. If no, it's just standard accounting or email, we go the buy route. This leads to requests for proposals, RFPs, vendor selection, and finally, configuration of the purchase tool.